Hello, today we are going to speak about uncertainty estimation in active learning. Firstly, we will speak about the formulation of the problem and why we should care. Secondly, we will discuss why active learning should work. Then we will talk about how to measure the quality of the active learning algorithms. And finally, I'll give a brief talk about acquisition functions in active learning. Why do we need active learning and the formulation of the problem? There are situations when there is a lot of unlabeled data and manual labeling is expensive. In such a scenario, learning algorithms can actively query the user or Oracle for labels. This type of iterative supervised learning is called active learning. Because the students selects examples, the number of examples to teach can often be much less than the number required in regular supervised teaching. The figure shows a typical active learning pipeline. We have a large untagged dataset U. From it, using the active learning algorithm, an object or several is selected to be marked up. Then this object gets to the oracle, for example, a person who marks it. Then this example is added to the current tagged dataset on which we retrain the model, and so in a loop. Active learning has many applications. For example, the following can be mentioned. Data labeling by assessors, for example, for information retrieval, text analysis, translation, speech recognition, image segmentation, for example, medical images, since qualified specialists are needed for marking, and video. Design of experiments in combinatorial chemistry, optimization of hard computable functions, for example, search in hyperparameter space, choosing a product for a marketing company. Why does active learning work? The figure shows a simple example. We have generated a toy dataset of two Gaussians, a binary classification with two features, figure A. If we select objects for marking at random sampling, then the classifier has an accuracy of about 70%, figure B. However, if you select objects using the active learning algorithm, which will be discussed later, then you can achieve a quality of 90%, figure C. Another example of why active learning should work. Consider samples from a uniform distribution on the segment from -1 to 1. Objects that are less than 0 belong to class 0. Objects that are greater than 0 belong to the class 1. If we randomly select objects for marking, then in order to achieve an accuracy for the class boundary of big O of 1 over k, we need big O of k objects. However, using binary search, you can achieve the specified accuracy with big O of log k objects. Assessment of the quality of the active learning algorithms. The quality of the active learning algorithms can be assessed using the following curve. On the abscissa axis, we will plot the number of samples, and on the ordinate axis, the metric on the deferred sample. In the figure, you can see a comparison of two active learning algorithms using these curves. This is uncertainty sampling, which will be discussed later, and random selection of an object. You can see that at the start of the training, uncertainty sampling achieves better quality on a small training size. For active learning, we need some rule by which we will select objects. Such a rule is called an acquisition function. The first kind of acquisition functions is uncertainty sampling. Its meaning lies in the fact that we take those objects on which the model is most uncertain. This is the most popular active learning strategy and is often used in practice. Least confident, select the objects on which the maximum class probability is minimal. Margin sampling, select the object on which the difference between the most probable classes is minimal. And entropy selects the object on which the maximum entropy is reached. Here we can see heat maps illustrating the query behavior of a common uncertainty measures in a three-label classification problem. Simplex corners indicate where one label has very high probability, with the opposite edge showing the probability range for the other two classes when that label has very low probability. Simplex centers represent a uniform posterior distribution. The most informative query region for each strategy is shown in dark red, radiating from the centers. We know that neural networks suffer from overconfidence problem. To solve it, we can use an ensemble of neural networks or Bayesian neural networks. Ensemble of neural networks are known to yield increased accuracy over a single model, allow useful measures of uncertainty to be derived, and also provide defense against adversarial attacks. So, the next kind of selection functions is ensemble-based uncertainty. In this case, it is assumed that we have an ensemble of big C models, and in fact, this is a generalization of the previous method. Ensemble entropy, we take the object on which the maximum ensemble entropy is reached. Ensemble diversity, another tractable approach for active learning. It is called BALD, Bayesian active learning by disagreement. Consider we have a Bayesian neural network or an ensemble of models. We can choose pool points that are expected to maximize the information gained about the model parameters. In example, maximize the mutual information. Mutual information is the measure of ensemble diversity. So, we are looking for areas where the models maximum disagree, where the model has many possible ways to explain the data. Consider the problem of classification into three classes. You can see total uncertainty, which is achieved via ensemble entropy, on the left. We are averaging the entropy here and get more accurate entropy estimation, but we couldn't distinguish between knowledge uncertainty and data uncertainty here. That's why using ensemble diversity is better, since we can measure knowledge uncertainty, which we can see on the right. Since the most popular models are neural networks, to efficiently utilize active learning, we need a batch of examples, but not a single one. Batch mode active learning is one of the most important practical considerations in active learning. One of the most important drawbacks of BOLD in batch settings is that it doesn't consider the information between selected examples. Let's have a look at the modification of the previous method. Batch BOLD is an extension of BOLD, where the mutual information between a joint of multiple data points and model parameters is estimated. This builds on the insight that independent selection of a batch of data points leads to data inefficiency, as correlations between data points in an acquisition batch are not taken into account. Intuitively, the mutual information between two random variables can be seen as the intersection of their information content. Let's have a look. BOLD overestimates the joint mutual information. However, batch BOLD takes the overlap between variables into account and will strive to acquire better cover of omega model parameters. Areas contributing to the respective score are shown in gray, and areas that are double counted in dark gray. Thank you for your attention.